Alright, in this part of the worksheet, we're gonna talk about more realistic way to form a confidence interval. From the first part of the worksheet, we talked about finding a margin of error, and the formula was margin of error, just a refresher here, C alpha over 2 sigma over radical n. Here, sigma represented the population standard deviation. In this case, wasn't 100% realistic because, again, we don't have full information of the population, so how are you supposed to know what population standard deviation is? So in real life, we don't really have that information. So right now, we're going to talk about more realistic case where we don't have the information about population standard deviation, but we only have information about sample standard deviation, which is denoted by S. So topic here is estimating population mean when sigma is unknown. So here I'm going to make a little comment. Instead, we'll use S, which is sample standard deviation. Sample standard deviation. So number 17, if you do not know sigma, then we're forced to use the sample standard deviation S, unfortunately, and it has tendency to underestimate the population standard deviation. So we'll do like we have to do one thing to kind of compensate that fact, and we'll do that by using this thing called student t distribution. So this is a new distribution we're going to talk about today. So this new distribution, student t distribution, is kind of similar to normal distribution, but there are some differences. So first, there's a different curve for different sample size. Its graph is bell-shaped also, and is symmetrical. That means when you draw the graph, it looks basically like Z. So it's bell-shaped and it's symmetric. That means like the left half looks almost like exactly like the right half. Part C is similar to the standard normal distribution. The student t distribution has mean of 0. So number in the middle is also 0. So that's similar. And unlike standard normal distribution, the student t distribution has a standard deviation more than 1. So it has more spread because it has a slightly higher standard deviation. As the sample size n gets larger, already when you look at the picture, it kind of looks like Z, but when you have larger sample size, it's basically, it's going to look almost like normal standard normal distribution. We have one more factor to consider here, the degrees of freedom. df is just n minus 1, means sample size minus 1. So when we use calculator to calculate a bunch of different stuff with t distribution, one of the things they're going to ask is the degrees of freedom, and it just n minus 1 for us. So we're going to have a new formula to find the margin of error. So we'll look at that first, and we'll talk about how to do it, how to find the critical value by using a calculator. So margin of error is going to look like E is equal to T alpha over 2. So notice that I'm not using Z anymore, I'm using T. And then I'll do S over radical N. I'm going to circle that. This is margin of error formula. Yeah, I'm going to make a comment. We are not using Z-score anymore. And also, instead of sigma, we have S, right? Instead of sigma, we use S. Again, the whole point of this formula is realistically we do not have sigma, or we don't know the value of sigma, so we're going to be using sample standard deviation S. That's why the formula is kind of same as before, except the different letters now. So our next step is, how do I calculate this critical value T alpha over 2? Before we use inf norm to calculate that. Here we're going to use different function key. This one is called inf t because we have student t distribution. So we'll do second, we'll go vars, which is the distribution, right? Distribution Then we'll scroll down to inv t option, and then it's going to ask you two things. It's going to ask you for the area. It's going to ask you for degrees of freedom, df, right? df is just degrees of freedom, which is just n minus 1, which is sample size minus 1. So that one I can just get that easy. The area, this part is slightly tricky. You notice that there's no left, center, right option. By default, it just takes in the area to the left. So when we try to calculate the critical value, we have to look at the graph and basically have to figure out the area to the left of the tail. All right, let's look at one of the examples. Let's look at number 23 here. Okay, it says a study found the body temperatures of 16 healthy adults. Okay, so that's like how many people they surveyed. So I feel like this is going to be my n, which is a sample size 16. The sample had a mean of 98.2 and standard deviation was 0.62. Okay, so sample mean was this. So I'm going to put x bar. And it says standard deviation of 0.62. So I have two choices here. Either I can label it as sigma, which is the population standard deviation, or I can label it as S, which is sample standard deviation. Here, this number came from the sample because it says sample had a blah, 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 blah. So I have to choose S because it's not population standard deviation. It is sample standard deviation. So I'm going to put S. So this is a case where sigma, which is the population standard deviation, is not given. So we're going to be using S. That means we're going to use the second formula that we talked about. So find the margin of error. So I'm going to mark the margin of error. This is going to be T alpha over 2 times S over radical n. So T alpha over 2 times S is 0.62 over radical n is 16, right? So our next step is to find the critical value T alpha over 2. So here we're going to use, let me make a side comment here. If the confidence level that's given to us is 95%, so this is T, 95% in the middle, that means 5% is left over. Because this graph has two tails, that means each tail gets 2.5%. So 100 minus 0.95, which is 0.05. But we have to split that into two portions because there are two tails. So each tail has half of that 5%. So 0.05 divided by 2 is 0.025. So that's area in one tail to the left. So that's basically what we're going to plug in. So here we'll do inv t. I'll put 0.025. So notice this is slightly tricky because I'm not putting 0.95 because it takes the area to the left of what we're trying to look for. So if 95% is in the middle, only 2.5% is to the left. Convert that to decimal, 0.025. And degrees of freedom is 16 minus 1 is n minus 1. So the 16 minus 1, so 16 minus 1. And it gets you negative 2.131. Again, I can just take that into positive 2.131 because negative 2.131 is here. The positive one is on the other side. So we'll just take the positive part. So I can plug that into t, the critical value t. So 2.131 times 0.62 over radical 16. And when you calculate this out, you're going to get 0.330. So okay, 0.33, that's going to be my margin of error. So the point of this question was that we need to notice that the standard deviation that is given to us was not a population standard deviation, but it was a sample standard deviation S. So instead of using Z, I used t-score. Now I want to talk about a shortcut to calculate the confidence interval right away. So how to calculate the confidence interval for the mean when sigma is unknown, right? Using your calculator. So we'll kind of do the same thing. We'll go to stat. Then we go to tests. So this basically gives you a little shortcut to calculate it, so you don't have to go through the whole process. You can get your final answer right away. Stats tests. In this case, we're going to use t interval. So that's option 8, t interval. Before we used a z interval when we are using z-score to calculate the critical value. Here we're using t interval because sigma is unknown. That means we are using s. That means you're using t distribution. That's why you're using t interval. So once you click that, it asks for x bar, which is sample mean, and it asks for sx, which is standard deviation for the sample. It asks for n, and then it asks for confidence level. So once you input those numbers, it'll get you the confidence interval right away. All right, let's look at number 24, and then I'm gonna have you, after that, I'm gonna have you work on a bunch of problems. Let's look at number 24. How do you find the sample mean and EBM, which is margin of error, E, if you're given confidence interval? So for example, let's look at simpler one first. What if your confidence interval was like 5 to 9 or something like that, right? So graphically, there's my 5, 6, 7, 8, 9, and then 9. So in this case, if I have to guess the sample mean, I know the sample mean is always in the middle, so they didn't say what the sample mean was, but if I know the confidence interval ranges from 5 to 9, I can guess, like, well, isn't sample mean right in the middle? So this must have been sample mean x bar. So how do you calculate the middle number right in the middle? Basically, it's an average. How do I calculate the average? Is 5 plus 9 over 2. And I calculate that, I get 7. So kind of knew that. So that's how I'll calculate the x bar given confidence interval. I just look at it graphically. I'll just pick the number in the middle. How about margin of error? Well, if this number is 7, this is margin of error E, and this is another margin of error E. Like, what's the difference between 7 and 9? Well, that's just a 9 minus 7, so that must have been just 2, because 7 plus 2 will be 9, 7 minus 2 will be 5, right? So in order to calculate the margin of error, we'll just have to look at the distance between the center and one of the end of the confidence interval. Just subtract one from the other one, and that's the length of that part. That gives you margin of error. So generally speaking, how do I calculate the mean? It's just the average of the lower end number and then the upper end number, or upper bound. So that. And EBM is just, well, we can do upper minus the mean. Then I can get the margin of error. Okay, I'm gonna have you pause now. I think you can finish the rest of the worksheet.